Hello friends, today we're going to be talking about linear functions and linear models. Now linear functions play a really important role in mathematical modeling because they're the simplest function we could use in order to try to model some data or some mathematical or social or physical phenomenon that we're trying to understand. And they're also the ones we're most familiar with, so that can be a real advantage as we try to learn how to work with data and finding a mathematical function to represent that. Now we're going to be doing this investigation of linear functions and models in the context of mathematical modeling. So let's begin by talking about the math modeling cycle for just a few minutes. There's 5 steps in the modeling cycle. The first step is to ask a question about reality, and then everything we do will focus around that question. Once we decide what we want to investigate or what we're going to explore, then we can make some observations and collect the corresponding data. So what are we going to do with that data? Well, our goal is going to be to try to conjecture a model or modify a known model based on this data. So for us, this will be like try to find a line which models the data. Then we're going to test that model against our data and then modify it as needed. We also then will repeat the last 3 steps in terms of making observations, conjecturing, and testing. Because new data might shed light on the phenomenon and therefore render our current model kind of obsolete. We need to kind of go back to the drawing board a little bit. So that repeating part is an important step. So let's begin our review of linear functions. So a linear function is a function that is of the form y equals mx plus b. So there's 2 parameters here. The first parameter is the slope m, and the second is the intercept b. Now we calculate the slope of a line through 2 points, x1, y1, and x2, y2, using the familiar formula with slope. So m equals y2 minus y1 divided by x2 minus x1. Notice that the order in which we subtract doesn't really matter. So we could equally as well do y1 minus y2 and then divide by x1 minus x2. The key thing to point out here is that the y's need to be in the numerator, the x's in the denominator. In the order we subtract the 2 data points must be consistent between the top and the bottom. Sometimes we refer to this as delta y over delta x, the change in the y coordinates divided by the change in the x coordinates. Or, in more common language, the rise over the run. How much it's rising vertically or falling vertically divided by how far we're kind of moving to the right. The vertical intercept b of a line is the y coordinate of the point 0b, so this kind of y coordinate, where the line intersects the y-axis. So let's look at the effect of these parameters m and b. There's 2 things to point out. First of all, whether the slope is positive or negative affects the tilt of the line. So line A has a slope, which we'll refer to as m sub a, which is negative. So it kind of tilts down. Okay, it's moving from the top left to the bottom right. Whereas in B, the slope is positive, and the slope in C is positive. Those both tilt upwards. They move from the bottom left to the top right. The other thing that the slope of a line can indicate is the steepness of a line. Notice that the slope m sub b is greater than the slope m sub e, which is indicated by the line B being steeper than the line C. So the steeper the line, the bigger the slope. The same thing goes true with negative slopes. The more steep the slope is in the negative direction, the larger or more negative the number would be. The effect of the parameter b shifts the line vertically. So in line A here, this would correspond to a b being positive. That vertical intercept, where it crosses the vertical axis, is positive. B, the line B, would correspond to having an intercept of 0 because it crosses the vertical axis at 0, and then line C crosses down here where it's negative, so that would correspond to B being negative. So the slope affects both the tilt and the steepness of the line. The vertical intercept B shifts the line up and down. So let's begin our discussion of linear models and using linear functions in order to represent or to model some data. So what we're looking at here is a graph of the number of Twitter users measured in millions as a function of time. So the units on the x-axis here, it says quarter of a year, so 11 would represent 2011, 11.5 would be like the second quarter or halfway through 2011, and so forth. And then on the vertical axis, we have the millions of Twitter users. So our first line of defense in deciding whether a model is reasonable for a data set is graphically. Do these points exhibit a linear pattern? Do they look like they fall on a line? So if we just kind of quickly sketch in a line, it seems like we're capturing the trend of the data. And so a linear model seems reasonable. Now, you might want to just stop right there, but many times our eyes can be deceiving. And there could be a little bit of a curve there that we're not really seeing. So we want to have kind of a secondary measure to kind of something more computational that can kind of back up this visual assessment that a linear model does in fact seem reasonable. If it doesn't seem reasonable, then we would stop right at this point. But it does seem reasonable in this case, so we'll continue on. So how do we numerically identify whether a data set exhibits a linear pattern? Well, we take advantage of the fact that any 2 points on a line have the same slope. So that means that in order to check for a linear model, y equals mx plus b, we do this by comparing the slopes of the lines through pairs of data points. Linear data sets have exactly or approximately the same slopes for any 2 data points. So because we're working with data, we don't expect that the points will all fall exactly on a line. So they won't have exactly the same slope, but we do expect these slopes to be pretty much the same or approximately the same. Now, in practice, what we're going to do is we're only going to look at the slope between consecutive data points. So we're only going to look at the slopes between kind of the first 2 points, the second and third point, the third and fourth, and so on. Any other combination would be equally as valid to consider. We choose consecutive just to keep the number of computations we have to do at a reasonable level. So let's look at our example of the number of Twitter users and decide if a linear model is in fact reasonable for this data set. So we calculate the first slope, m1, by subtracting the first 2 output values, 85 minus 68, and then dividing by the difference of the input values, 11.25 minus 11. Plugging this into our calculator, we will get a slope of 68. So now let's look at the second and the third, so kind of our next pair of data points. So we'll call this M2 for the second set. So we take the difference in the output values, 101 minus 85, and then the difference of the input values, 11.5 minus 11.25. And if we plug that into our calculator, we get 64. For the third and fourth data point, this will be our third slope. We get the difference of the output, 117 minus 101. We'll divide by the difference of the input, 11.75 minus 11.5. We put this into our calculator, we get another 64. And then finally, for this last pair, we get 185 minus 117. We'll divide by 12.75 minus 11.75, and that once again gives 68. While these numbers aren't exactly the same, which we wouldn't expect when working with data, we do have to decide whether or not they're approximately the same. And this is where things get a little bit more tricky, or subjective, you could say. Because we have to decide essentially if the biggest difference between them, say in this case 4, between 64 and 68, we have to decide if that's a big number, a big difference. Well, So we're thinking about a difference of 4, and the slopes themselves are 64 and 68. So that doesn't seem like a very big number. If we look at 4 in the context of our output values, we're looking at numbers like 68, 85, 185. 4 doesn't seem like a big difference there. So the number 4 isn't a big number in the context of the slope, 64, 68, nor is it a big number in the context of the output values. So we'll say that these are in fact approximately equal to each other. And so a linear model is reasonable. But now we have to decide what linear model are we going to use. So we've calculated all these slopes between consecutive data points. Which one do we use as the slope of our line? Well, none of them would really capture the data perfectly. So what we'll do is we'll average them. We'll kind of use a little bit from all of them to decide on the best slope for the whole data set. So to compute the slope, we take the slopes between consecutive data points that we just computed. So in our Twitter example, M1 plus M2 plus M3 plus M4, and then divide by the number of slopes, 4. Once we've decided on our slope, then we need to find our vertical intercept. And so we want to do the same thing here. We don't want to favor any one data point more than the other. So what we'll do is we'll find the vertical intercept that correspond to each data point using the slope we just found, and then we'll average those intercepts together in order to find the intercept for our line. So let's look at our Twitter example one last time. Remember, our slopes were 68, 64, 64, and 68. So if we average those together, we're going to get a slope of, it'll be 68 plus 64 plus 64 plus 68, and then we'll divide that by 4. If we put that all into our calculator, what we find is that we get a slope of 66. So at this point, we've decided that our line will be y equals 66x plus b. And now we need to go use our data points to decide on our value of b. So remember, our line at this point was y equals 66x plus b. So we're going to plug in our first data point. So the y value would be 68. We'd have 66 times our input 11 plus our intercept. I'm going to call the intercept for this first data point B1. If we take the 66 times 11 and move that to the left, we get 68 minus 66 times 11 will be equal to B1. So that means that B1, if we plug this into our calculator, will be negative 658. Now we repeat for our second data point. So we plug in our output value of 85. It'll be 66 times the input value of 11.25 plus the intercept, which we'll call B2 since it's the second data point. We'll move the 66 times 11.25 to the left. So that gives us 85 minus 66 times 11.25 will be B2. Plugging that into our calculator, we get B2 is equal to negative 657.5. Now at this point, I want you to go ahead and press pause, take a moment, and try to find B3, B4, and B5 for these last 3 data points on your own. And then here in a second, go ahead and resume the video and see if you got the same value as me. Okay, so for B3, I got negative 658.5. B4, I got negative 656.5. And B5, negative 657.5. Oops, I'm sorry. On B3, I got a little too much there. No 0.5, just 658. Okay, so to find my value of B that I'm going to use, I'm going to take these, got a little ahead here, B1 plus B2 plus B3 plus my B4, my B5, and I have 5, so I'm going to add them up and divide by 5. Doing this, using my calculator, I get negative 657.7. So that means the equation of my line is going to be y equals 66x minus 657.7. So the next step in our modeling cycle is to test our model against our known data. So if I make a plot of the data points that I have, my 5 data points in the line I just found, what I see is that the line I found captures this data reasonably well. Now, the nice thing about having an equation for this situation is that I can use it to make predictions. So I could find, say, the value, the expected number of Twitter users in 2015 by taking my slope, 66, times the year, 2015, which we're using just the last two digits, minus 657.7, and that would give me an expected number of users of 332.3 million. But the thing is we don't know how accurate this is. So we don't, I mean, we could go try to find the number of Twitter users in 2015 and see how reasonable this is, but it may or may not be reasonable going forward. I mean, if I put in 20 for 2020, would I get a reasonable number or not? At some level, we don't expect this trend to continue indefinitely, but it's not clear how long it might continue. If you go kind of back in time and you plugged in, say, oh, I don't know, 0 corresponding to year 2000, we would get a predicted number of users of negative 657.7 million. So this intercept, it may seem surprising at first, and part of that is that it predicts the number of Twitter users before Twitter even existed. So we would expect to get a silly value there. So it only makes sense in the context of the data and that we have. And outside of that, we're really extrapolating from the data, and we can't rely on those predictions very reliably at all. Well, that's it for linear models and linear functions, and I wish you guys great success as you work through some more examples and try to solidify this material.